Section 1 of Chapter 9 is about first-order differential equations. Now, we've actually solved differential equations before. We just always called them initial value problems, and we'll get to some of those examples in a minute. But before we do, we have some definitions to go over. First of all, just to remind you, in the expression dx over dy or dy over dx, the dx and the dy are called differentials. And that's where the name for differential equations comes from, because a differential equation is an equation involving one or more derivatives, like dx over dy or ds over dt, of an unknown function or functions. The order of a differential equation is the order of the highest derivative in it. In other words, if you have the only derivative in the equation is a first derivative, dy dx, then it's order 1. If it's a second derivative, f double prime of x, then it's an order 2, and so on. Now, the solution to a differential equation is whatever function makes the equation true. So the variable we're solving for is actually a function. And what's different about these from other equations we've solved is that when we plug that variable in, we're going to have to plug in the function itself as well as one or more of its derivatives and see if it makes the equation true. So let's look at an example of a differential equation. Okay, so for example, the equation dy dx minus y equals e to the 2x is an example of a differential equation. And in this example, we're asked to verify two of the solutions. Now remember, solutions to a differential equation are functions themselves. So we want to verify that y equals e to the 2x is a solution. And we also want to verify that y equals 3e to the x plus e to the 2x is a solution. Okay, so this is just a matter of plugging into the equation. So the equation we have to start with is dy dx minus y equals e to the 2x. We know to verify y equals e to the 2x, we need to plug into this equation. So dy dx becomes the derivative of e to the 2x when we plugged e to the 2x in for y, minus y is e to the 2x, and we want to confirm that that equals e to the 2x. Okay, so what is the derivative of e to the 2x? Well, this is a chain rule, so we're going to have e to the 2x times the derivative of 2x, which is 2. So we have 2e to the 2x minus e to the 2x equals e to the 2x. Subtracting here, these are like terms, so we just get 1 e to the 2x equals e to the 2x, which is true. So we just verified that that is a solution to the given differential equation. The second potential solution is y equals 3e to the x plus e to the 2x. Again, plugging in means taking the derivative of y, dy dx, but in this case y is 3e to the x plus e to the 2x. Then we want to subtract y. So again, 3e to the x plus e to the 2x. And this is supposed to turn out to be e to the 2x if this is a solution. Taking the derivative, the 3 remains the same. Derivative of e to the x is e to the x, plus we already know to take the derivative of e to the 2x, we're going to get 2e to the 2x. Distributing the negative here, we have minus 3e to the x minus e to the 2x. And this should equal e to the 2x. We Hope. These cancel, and again we have 2e to the 2x minus e to the 2x is 1e to the 2x, which is equal to e to the 2x. So we're done. So both of these are solutions to the given differential equation here. Here we see figure 9.1.1, which shows select curves from the family of solutions of the equation that we just looked at. dy dx minus y equals e to the 2x. Now the two solutions in particular that we looked at were c equals 0 here in brown. For c equals 0, the equation of the function, which is the solution to the differential equation, is y equals 0 e to the x plus e to the 2x, or in other words, when c equals 0, you're just looking at y equals e to the 2x. And the other case that we looked at was when c equals 3 here in yellow. Now this isn't a graph of all of the possible solutions, but it does show you the general shape of the solutions for different values of c that are selected here. Now, as I mentioned before, we actually have solved differential equations before. We just called them initial value problems. And what we mean by initial value problem is a problem in which you're given a differential equation to solve as well as a point on the graph of the solution. This allows us to narrow down our search to one particular curve rather than a whole family of possible solutions. So let's look at an example of a kind which we have actually solved before. The instructions say solve the initial value problem. And we're given dy dt is equal to, plus t is equal to 2. We're also told that the function y we're looking for contains the point 0, 1, or in other words, y of 0 is equal to 1. Okay, so we're given information about the derivative. We want to find the original function. Solution. In this particular case, it's easy enough to rearrange the equation so that the derivative, we see that the derivative is 2 minus t. And then we know that we can just take the antiderivative of each side with respect to t. Which gives us the antiderivative of y, of dy rather, is equal to the antiderivative of 2 minus t dt. Or in other words, y plus some constant, I'll call it c naught, is equal to 2t minus t squared over 2 plus some other constant c1. Now normally we don't write c naught and c1 because moving c naught over to this side, we can just combine them into one overall constant, c. Okay, so what we've done so far is the first step. We found the general solution to the differential equation. Now we're going to use the information that this solution satisfies y of 0 equals 1 in order to find the particular solution for this initial value problem. Alright, so to say that y of 0 equals 1 means that when t is 0, y is 1. So plugging into our solution, we have 1 equals 2 times 0 minus 0 squared over 2 plus c, which means that c is equal to 1. So the particular curve that we're looking for is y equals 2t minus t squared over 2 plus 1. Now, one thing that we might want to do is just to confirm that this is in fact a solution to the original differential equation. And how could we do that? Well, we just plug it in as we did before. So to check, we're going to check that dy dt plus t is equal to 2. Well, dy dt is the derivative of y, which is going to be 2 minus t. We're adding that to t, and in fact that does equal 2.